Hello, everybody. Welcome to this knowledge sharing session today. Working through Natural Hazards Research Australia, working with the University of Queensland and Energy Networks Australia. We'll be hearing some of the work that's being done in one of the projects, strengthening energy networks to withstand severe wind and storms today. Firstly, let me again thank everybody for coming today, and we just pay our acknowledgements to First Nations folks around the country. Always thinking about the long lines of teaching and learning across the different parts of the country that we come from. My name is Brendan McAtee. I am over in Perth as one of the node research managers. So I'm in Whadjuk Noongar country today, just a little bit out of Freo, Walyalup. So thank you and pay those respects to any of the First Nations folks online today as well. You can see there that of our pieces that Natural Hazards Research Australia has, Manawana Punjin in our hands. It's a very interesting and detailed little graphic that talks again about all the different places that we are across the country and the significant icons from there. So today, as I mentioned, we're talking about the Strengthening Energy Networks to Withstand Severe Winds project. That's a piece of work that Natural Hazards Research Australia invested in, working with Energy Networks Australia, being performed by the University of Queensland and a research team that Associate Professor Matt Mason will talk a bit about. So Natural Hazards Research Australia likes to enable this kind of research across the emergency management sector and natural hazards, disaster risk reduction sectors. This project in particular, looking at current impacts of severe winds on energy networks and what the future might hold for there. Our research that we like to enable is about research which is useful, usable, and used. So we're really, as a centre, really focused on creating that impact and making sure that the work that we do gets into the hands of the people who need to use it to make a difference in those sectors. Shortly, I'll throw to Craig Savage from United Energy and Energy Networks Australia, just to give a bit of that end user, that industry perspective on the work and the need and the importance of it. Then I'll pass over to Associate Professor Matt Mason and Dr. John Holmes, who are key people of the research team, to talk about the work that they've been doing. We'll have some questions after Dr. John Holmes' presentation. We might have a little Q&A session, so feel free to put some questions in the chat there, or we're going to ask them at the end of John's presentation, and we'll talk a little bit more about any other questions or comments at the end of the session as well. So we should have a really interesting session this morning. I've seen a bit of the work that the team's been doing, and I think it's really interesting, and I'm sure you'll find it the same. What I might do now is throw over to Craig Savage, just to give us that bit of that industry perspective on this piece of work and its importance. Craig, I'll throw over to you.
Thanks, Brendan. Good morning, good afternoon all. I'm representing ENA today. I'm currently the ENA's chair of Reliability and Resilience Committee, even if there's not actually a committee. And therefore, I think I'm the lead partner in this project, I suppose, representing ENA. So ENA have been partners with NHRA for, I understand it's about 4 years now, give or take a couple of months, through ENA's Asset Management Committee. And it's kind of extending the relationship that we had with NHRA before they were NHRA, where many of you would have had relationships with them in the past about bushfire. Last year, we were successful in getting this project funded, focused on the impacts of severe wind and storm events on network assets. And to some respect, it was in response to having resilience added to the national electricity objectives and a number of high-profile incidents at both transmission and distribution level. So with climate change forecasting impacting our services more frequently, more severely in the future, it's kind of a key project in getting ahead of the current and future storm impacts, so we can all make our own informed decisions based on a common industry understanding, which this project is hopefully going to give us a common basis for forecasting wind impacts on our networks into the future and customer impacts more specifically, and therefore being able to base resilience-based investment and alignment between us all is quite important when dealing with the AER. So you're not here to listen to me, you're here to listen to Matt. So that was briefly why ENA are in it, and more specifically for me, why UE, City Power and Powercor are in it as well. Hopefully you get the same out of it as I'm hopeful of getting out of it today too, in giving it strengthening my base of knowledge as to where we're heading with this.
Thank you, Craig. Yeah, thank you for that introduction and that description of where the it puts that emphasis on this, that this work is to get into the hands of users to solve a problem for the industry. I think that's really an important emphasis to make sure that we keep thinking about that utilization aspect. And this is pretty strong. So with that, I'll throw to you, Matt. Briefly introduce yourself and John, and take us through the work that you've been doing.
Yeah, thank you, Brendan. Thank you, everyone, for joining. My name's Matthew Mason. I'm at the School of Civil Engineering at the University of Queensland. A couple of people on the call I can see. What we're going to talk about today really is a couple of the early parts of this project that we've started undertaking. The project itself is a sort of a collaboration between researchers at the University of Queensland, the University of Melbourne, JDH Consulting, and Weather Solutions. And as you've already seen, Energy Networks Australia is the industry partner on the project. What we're going to do today is really talk about sort of, as I said, two of the main things we've been working on in the early part of the project. The first is what John will talk about, and this is a review of some of the design codes and standards that get used for the design of both transmission and distribution lines, and looking at potentially how some of those might be able to be modified or updated to account severe wind impacts. We'll have a short Q&A after that if there are any burning questions for John. And then I'll talk about the second thing that we've started on the project. And this is to develop a national database of outages and interruptions to both distribution and transmission line due to severe wind events. And we'll talk a bit about how we've progressed on that. And I will have a request for those listening as to for a bit of help to try and get that sort of finished off. But for now, I'll turn over to Dr. John Holmes, who will take us through the first part of the talk.
Yeah, thanks, Matt, and thanks, Brendan and Craig, for the introduction earlier. I'll be talking about design codes and standards relating to power infrastructure, and I did produce a 8-page document. I think middle of October, I think, was the final version. So I suppose codes and standards are loved by civil and structural engineers for designing. I think the advantage of it puts people on a level playing field, or puts different operators on a level playing field when it comes to design. I guess transmission and distribution lines are no different to other structures such as buildings, communication towers, etc. So these are the topics I'll be talking about for the next 15 or 20 minutes. You can read them there. I won't go through the detail until we come to them. So the first one is on regulation, just a couple of slides and the sort of background to why we're using codes and standards of a certain designation and what their relationship is. So most of you will be aware of the AS/NZS 7000, which is overhead line design. I think the first edition was 2010. This is a current edition still, I think 2016. Now, there's a relationship between that one and the Structural Design Actions Wind Action Standard, AS/NZS 1170.2. which Matt and I have been involved in for quite a few years. And in my case, even to the last century, back to the last century, I was starting to get involved in it. So, but the thing about it, as I'll show on the next slide, is that 1170.2 explicitly excludes transmission lines and distribution lines. So it's a problem. So this is a relationship between 1170.2 and the National Construction Code, which despite its name does not cover anything except buildings. Used to be the Building Code of Australia. Now it's just Volume 1 is still the Building Code of Australia. And the way 1170.2 operates, pretty much have to, it gets called up as a source of loading, wind loads in this case, but other types of loading are called up other parts of 1170. So the National Construction Code doesn't write its own rules for structural loading, so it relies on Australian standards to do it. One of the ramifications of that is that they're very fussy about how the standard is written. 1170.2, you've got to use the word shall. You can't use should or may, and it has to be a well-defined path as far as they're concerned. So that's the relationship between the NCC 1170.2 and 7000. Now, what about the actual regulation of the structures? Now, I know the energy networks are regulated from a financial point of view and electrical point of view, but it's not. I'm not sure how they're regulated by how the structural side of it's regulated. It seems to me that it's largely self-regulated by the networks, and that probably goes back to the old days when each state had its own state government had its own control of its own network. But it's quite different for 1170.2. As I mentioned earlier, it's regulated through the NCC, which is effectively the law of the country with regard to buildings. So there's a difference there. 1170.2, as I mentioned earlier, excludes, page 1, clause 1.1, excludes tornadoes and excludes transmission line structures. Now, we know that tornadoes can actually damage transmission line structures as well, so it's a bit of a problem. That doesn't mean you can't use it. I mean, I think it's got a lot of useful information on things like shape factors for lattice towers and tubular towers, which you probably need to use because I don't think that's covered in 7000. It refers to 1170.2. So even though 1170.2 excludes transmission lines, it's not. We try to provide useful information in there for other structures. Now, AS 7000. I said the first edition was 2010, and I wasn't on the committee myself, but I had quite a bit of input into it through Henry Hawes from PowerLink. He might have been the chairman of the committee, I'm not sure, but I knew him quite well, and he asked me to provide quite a few bits and pieces with regard, especially in Appendix B for wind loads. But in this project, I've actually gone through the front end of the standard, which I wasn't really familiar with before, and looked at sections 6, 7, and 8, and I've made a few comments on those in the 8-page report I did. And I think one of the issues is that those earlier sections don't really reference the Appendix B in the right places. I think maybe they're written separately or something. So it could be a bit of editorial improvement, I think, there maybe. Let's just go to what's in Appendix B. And again, in 15, 20 minutes, I'm not going to go through every detail of wind loading. Just pick out a few highlights, if you like. Now, you'll see this map in there, which is not the same as the zonal map in 1170.2 for Australia. It's a special map that we produced for 7000. Really just tells us the type of wind events that are dominant in various parts of the country. You see, the middle part of the country is roughly 200 kilometers from the coastline. It's convective downdrafts are the dominant extreme wind event. So these large-scale synoptic winds, I'll show you a couple of slides on the different profiles that are produced by these type of events. But the synoptic winds are sort of large-scale events such as East Coast lows and frontal events in the southern states. The convective downdrafts are much shorter duration, and they last maybe a few minutes, whereas synoptic winds can probably last all day, typically, at a high level, strong level. So this is... I think in Appendix P, it suggests that in Zone 2, you need a design for convective downdrafts because they're basically the sum total of extreme winds. The synoptic winds are very light and sort of not much interest as far as structural loading is concerned. But you notice Tasmania is pretty much dominated by synoptic winds, whereas the green area, the Zone 3 as it's called, in this one is got a sort of a mixture of synoptic and convective events, which makes it a bit messy to codify. That's nature. Again, I'm not going to give you a lesson on meteorology in 2 slides, but just to give you some idea of what we're talking about here. The large-scale synoptic winds, the wind engineers sort of call them boundary layer winds because they can be reproduced in a boundary layer wind tunnel. It blows over long distances over the rough Earth's surface. If it is rough, you've got buildings in there and trees, creating some turbulence and a profile, as you see on the right there. So the wind speed is varying with height, up to probably something of the order of 1 kilometre when it's fully developed. So we're talking about extratropical gales is one term that's used. It also covers east coast lows that affect most of New South Wales and parts of southern Queensland, I think, and also tropical cyclones, which of course in the north part of the country, also known as hurricanes and typhoons in other parts of the world. Whereas a convective downdraft, which affects this middle part of Australia, 200 kilometres or more from the coast, but also other parts, but it's the dominant for the middle part of the country. It's created by convection, you can gather from their name, which is warm, moist air getting pushed up under convective forces to something of the order of 15 kilometres above the ground, then rapidly cooling, may produce hail or rain or both, and then becomes colder and then falls under gravity, essentially, and then eventually hits the ground as something like a jet hits the ground. And it produces a frontal, small-scale frontal storm that gives a profile, as shown on the right there. So the peak is probably it varies from event to event, but it's probably of the order of 50 to 200 meters above the ground. So instead of the 1,000 or so profiling with the wind increasing, it's sort of at some point it'll start dropping off. And of course these are short duration events, as I said, maybe 3 to 4 minutes typically, and affecting maybe a couple of kilometers wide. In terms of transmission line spans, I think we're talking about 3 or 4 or 5 spans typically. So these are happening quite often. Often they don't get detected. You're lucky if it hits a Bureau of Meteorology anemometer, although we can find them, we certainly can find them, but I'm sure we miss a whole lot of them because they haven't got that big a network of anemometers around the country. But these days everybody's got a camera on their phone, so we're getting a lot more pictures of them. So you can see the sort of vortex that's produced horizontally on the left. So that actually came from the US. It's quite an old set of images. But you do notice a transmission line in there, or a couple of transmission towers in there. So they certainly can envelop up 40 or 50 metre high towers. The one on the right there I just picked up this year, a couple of months ago, at the AFR, Australian Financial Review. Somebody managed to get a picture with presumably their mobile phone. And again, you see some look like distribution lines or something on the right there. I think they're not leaning over like that. It's probably distortion of the camera. But you see the lightning in there. So these are associated with thunderstorms typically. Though you do get dry microbursts as well, which are probably not quite the same, but they do produce this downward jet of air. So why are we interested in those events? Part the fact that they're the dominant event in the middle of Australia, they do damage a lot of transmission lines. Span reduction factors, so moving on. So this is something you'll find in that Appendix B. What is a span reduction factor? Basically, if you're dealing with synoptic winds, which is where the idea came from, it allows a reduction in the peak load, assuming that the peak pressure does not occur even over one span in synoptic winds. Just the fact that we've got turbulence in there, which is gustiness, producing fluctuating pressures that don't occur simultaneously. The peaks don't occur simultaneously over even 500 meters. Could be typically 100 or 200 meters maybe. But in general, if you're in a rougher terrain, which gives you higher turbulence or gustiness, then you'll get a reduction in load through a lower reduction factor. On the other hand, these convective downdrafts, for the information we have got, which is a bit limited, but they certainly indicates that the turbulence is actually effectively lower because the wind is not blowing over this rough terrain. It's coming down from above, so there's not a mechanism for generating as much turbulence in the flow. So that means you've got lower turbulence, you're going to have higher span reduction factors, which means less reduction. And the result of that is we have figures in the Appendix B of 7,000. This is for synoptic wind span reduction factor. Some of you may be familiar with it. So what it's telling you, that figure B5 there, is that if you've got a span of 500 meters, you're getting a factor of 0.63. So that's like a 37% reduction in load just due to the fact that you've got this turbulent wind acting over a span of 500 meters. So there's a significant reduction. And you find around the world that, the synoptic winds tend to be more dominant, that these get used very widely, or similar values get used very widely in other parts of the world. So these are valid for these large-scale synoptic winds. But on the downdrafts, because the turbulence is effectively lower, figure B6 in Appendix B gives you a reduction of only 9%, a factor of 0.91 for that 500-meter span. So I think it's about a 40% increase, effectively a 40% increase in load. So if you talk about the same wind speed, so you might be talking about 40 meters per second gust, you're getting a 40 meter per second gust in a downdraft, or a convective downdraft, is worth 40% more than the same wind event at a point, the same 40 meters per second at a point for synoptic winds. So it does make a difference. Actually, that probably explains why we're getting a lot of these failures due to those type of events, and not so much due to synoptic winds. Right, now moving on to line orientation and length effect. There is a clause in AS 7000, it's sort of informative clause really, that says, as you can read, the return periods are appropriate to individual structures affected by either wind types. So that's in 1170.2, which is basically in there for buildings. We're interested in designing a building which effectively is at a point, a single point. But we're talking about a transmission line which may go for 100, 200, 500 kilometers even these days. Those return periods won't reflect the risk or the probability of a wind event such as this convective downdraft crossing somewhere along the line rather than at a point. And the result of this is, if you don't really take account of that, you might get some failures. And last year we had a few failures. Victoria and Broken Hill, New South Wales, and some of you may remember those. This year seems to be a bit quieter, fortunately. But if you think about it, these storms are, as I say, a couple of kilometers in width. But if you put a transmission line in there of 100, 200 kilometers long, it's like a fishing line, and you're catching these things periodically. So you probably need to be aware about it. I'm not suggesting that you need to design for, 1 in 500 or something for a whole line, because that wouldn't be economic. But people, I think designers should be aware of the risk of these events occurring. Now, going back to the even to the late 90s, of myself and Stephen Oliver, who's probably not on the line today, but he's part of this project, produced a model for the risk, calculating the risk along a line like that. And it started off just simply one of these events. We simplified it with a rectangular footprint with a certain width and a certain length, and looked at the chances of that footprint intersecting with a line of length L mathematically. And Steve actually wrote a computer program for Electronet. I see Roger's on the line there. He's hopefully using it. He might be able to tell you how he finds it. But I think it does give you a pretty good idea of the sort of risk on the line, depending on its length and also its orientation, north, south, east, west, or whatever. Now, from a code or standard point of view, you're not going to embed a computer program in the code or standard. We haven't got to that stage yet. But one of the things I did for Electronet, I'm not sure they use this, but look into the future maybe, putting something like a line length multiplier in the standard, which does recognize in a standard, maybe 7000 or somewhere else, where it does recognize this length effect. The line orientation can be taken account of through the wind direction multiplier that we have in 1170.2. So it could be something like this, and I've got to put some numbers on there to show how this could be used. Now, don't take the numbers seriously. These are just sort of notional numbers. Not necessarily recommending any particular numbers for this. Just those constants in there were like a fitting to the results of the computer program. wind risk that Stephen Oliver produced. So this might be an example here. So you have a line of length 120 kilometers. Let's say you want to design for 1 in 20 years. Well, this is average recurrence interval. 1 in 20 years average recurrence interval of reaching a certain wind speed on a line of length 120 kilometers. So the way you would work that out and account for the length effect is you'd look up 1170.2 and V20 and region A5, which is mainly South Australia and Victoria, was 37 meters per second. So that wouldn't be if you're trying to design for the whole line, you wouldn't use that wind speed with a certain risk. You'd try to adjust it for this length effect. You'd include the direction multiplier, which is in 1170.2, which is for an east-west line is averaging out as 0.875. So then you apply that formula ML and put in the RL and the length of the line L 120. It gives you 1.33, and then your design wind speed, taking account of MD and ML, would be 43 meters per second. So that should be, as I say, don't take the numbers seriously, but that would be, for this notional line there, the risk of, the wind speed you need to design the structures all the way along the line in order to limit the risk to 1 in 20 years, or 20-year average recurrence interval. All right, moving on. How are we going for time here? Probably another 5 minutes or something. So moving on then, you can ask questions about that maybe in a bit later. The drag coefficient for conductors, important thing. The wind drag, how you relate the wind speed to the force on the conductor. Just a 1 meter length of conductor. The span reduction factor allows you to reduce the overall load, but for the cross section of the conductor, most of the stuff we've shown on this graph here, this is out of the, I don't think it's actually in the Appendix B, but it's pretty well-known graph. It's in other ASCE documents, etc. These tests were done in the United States, putting sections of conductors in a wind tunnel. There's 11 or 12 or 13 different types of conductor. So a bit of spaghetti in there, so it varies quite a bit depending on the particular cross section and how they're wrapped. But on average, you're looking at a value of 1.0, and that's what is stated in AS 7000. A lot of other codes and guidelines, such as ISC, American Society of Civil Engineers, produces. So it's a pretty well-known number for the average sort of drag coefficient. What I discovered writing this review for you, the task 3, is that that might be okay for transmission lines, but the abscissa on this graph is the Reynolds number, which is a fluids mechanics term that you may not be too familiar with. Basically, it's the wind speed times the diameter of the section of conductor. Well, when you're talking about distribution lines, you've got a lower diameter, set of diameters. So actually the range is more like these values. The range of Reynolds number is sort of around 10 to the 4th to 1 by 10 to the 4th to about 3 by 10 to the 4th. And in that range, that value of 1.0 is on the low side. It's probably more like, you can imagine drawing a line through about 1.2. So it's more like 1.2 on average rather than the 1.0. So the 1.0, I think, really was for transmission lines and larger diameters, possibly higher speeds. You're higher up. The lines are higher up above the ground where the wind speed's higher. So something should be looked at, I think, in the future. So these are a few of the anomalies that I think you'll see in the report there that I've just highlighted that occur to me with respect to 7000. It hasn't been revised since, 2016. So if it does get revised, then a few of these things should be looked at mainly. I'm going to be running out of time, so I won't go to the detail of them. But again, it's in the report that I produced there. And I think after the first edition of the report, there's some comments came back and said, well, you've covered transmission lines themselves and towers. What about other infrastructure such as...
substation gantries?
Sorry?
Substation gantries? Talking about substation structures?
No, sorry, I had a mental break here. Substations, electrical substations, we're talking about here, sorry. How would you deal with those? And of course, that's difficult. It's the problem we have come across before, though, for a similar problem with any kind of industrial structure. You've got a whole lot of elements in there, and things like, power stations and refineries, etc. And each one has got its own contribution to the overall wind load. But you're getting shielding and interference between one part and another. So it's very hard to codify this because they're all different from each other. But what we've got in 1170.2 is a method which I think people have been able to use, they tell me. I've had a lot of feedback from it since we put it in there. This is a way of doing it. What we do have in 1170.2 is a method of dealing with a series of building frames. As I said, the standard is written basically for buildings, and you might have a series of frames erected without the cladding around the building. So and they might be exposed to the wind for a certain period. So there's a way of dealing with that. You have the windward one, and then that's shielding the downwind ones. So you have a shielding factor for the downwind components. So if you treat this like a series of frames, doesn't look much like it, but you can imagine doing it this way. You might divide that system into 4 or 6 planes normal to the wind direction, and try to estimate the load on each of the components there, each of these so-called frames or planes. If you don't do it that way, if you just, and I've seen this happen a bit, especially in the petrochemical industry, with people try to deal with something complicated like that, and they just add the wind drag on the individual elements, add them all together, and you can be hugely conservative if you do that. And we've seen factors of 5 and 10 on the correct loads, where occasionally these have been put in a wind tunnel and these kind of things, and we actually are able to measure the complete loading of a complicated group of structures like that. So we need some way of dealing with it, and this is about the best we can do at the moment, is as following those notes there. That's all I had to say. Hope I haven't gone too far over, if at all.
Thank you, John. Really interesting stuff, getting into some of the detail. I was just tracking the questions and comments in the chat.
Okay.
A couple in there from Raju and from Francis. So Raju mentioned that he's been using the model that you and Stephen developed. The question
good.
from Francis around that for either yourself, John, or for Raju, using the wind risk model from John, how do the wind speeds it gives you compare to the values following AS/NZS 1170.2? Is it higher or lower or the same? So either yourself, John, or perhaps Raju, if you'd like to comment on that, if we do that quickly, and then we might throw to Matt to get on to some of the other content.
I'm happy to take this if John allows me. John?
I don't know. Was that a question for you, Raju, or for me? I'm not sure.
Yeah, for me, but I'm happy to. We both developed this solution anyway. So I'm happy to take this one. Let me spend maybe 30 seconds. 1170.2 provides the design wind speed for an isolated location. Our wind risk model allows the account for the line length, line orientation, and the past incident, and then projection of the past data to the future. For that reason, majority of the cases where lines are positioned north, south, or inclination, we always get the design wind speed higher than 1170.2 for the given reoccurrence period. We have found few line where the short line and line are east-west. That means along the line direction has a less effect. In that case, we find comparable to 1170. There's no case we found where the wind speed calculated by this model is less than 1170 value.
Great.
That's it.
Thank you, Raju.
Thank you.
We might move on in the interest of time to Matt, if you'd like to give your presentation, but if we'd like to follow up any of those questions, we'll have a little bit of time at the end of Matt's one as well. Thank you, everybody. Thanks, Matt.
Okay, thank you, John and everyone. So I'll talk about the second, another of the tasks as part of this project, and this is really to develop a national database of outages caused by severe windstorms. So as I said before, I'll talk about how we're progressing and then have a request for those on the line. So what we're trying to do here is build a database of outages on both the distribution and transmission networks that have historically occurred due to severe wind events. And importantly, I think what we're trying to do is we're trying to assign the type of wind event that has caused the outage. Because as John mentioned, we do have the type of wind event that we have is quite important for how the wind loading will transfer onto the line and therefore the expectation of damage. So the way we're doing this is really for transmission, what we're looking at is the category analysis regulatory statements that are put into the Australian Energy Regulator, where you have sustained interruption. So that's giving us the information on the interruption that has occurred on the distribution networks. And I'll talk a little bit more about exactly what of that we actually take. And for the transmission interruption, there we tried a couple of approaches here. So SIGRE has a database of failures, which, working with the industry partners, particularly PowerLink on this part of the project, we sort of got to the point where we realized that that was not really updated. So working with Damien Scott at PowerLink, for any of the transmission people online, hopefully he's been in contact with you. What we're trying to do is collect all the interruption data over the last few years and add that to essentially the data that exists within the SIGRE database so that we can have a complete list of outages up to this point in time. So the reason why we're doing this is really to understand what type of wind events are causing the outages. So we all know that when we have severe storms, irrespective of their type, we tend to have some interruption to power. But what we want to really understand with this database is how does that change across the country and what types of wind events are important for the different network or the different networks, both transmission and distribution around the country. And intuitively, I think each of the network service providers will know the types of events that are important for them, but we see it as quite important to aggregate this all together so that we can look at this on a national scale as opposed to just an individual network. And the other thing that we're going to do with this is really to inform another output of the project, which is the development of a risk model, very similar to what Raju was talking about the Electranet is using. At the moment, we're looking to develop something similar that we can sort of have as an output of this project. So here's a summary of all the distribution and transmission networks around the country. The ones that we've got a tick are where we have the interruption data already. And this is we largely have this from the period from 2009 to 2024. And this is essentially the distribution networks. So we've been able to get through the RIN analysis, the RIN data that's been provided to AER, we can get it for all the distribution networks that fall underneath that. But we've also been able to get through the Project Management Committee, we've been able to get some data from Western Power, and through another colleague, we've been able to get some from the Northern Territory as well. So we actually have a pretty complete database of interruptions at the moment for the distribution network, but we're still working on getting the outages on the transmission line network. So I think that's something going forward that we would like to, if Damien hasn't been in contact with any transmission people here, I'd be very happy to sort of start that conversation so we can get that data. And just as sort of a snip of what we're taking, so the information that's provided by each of the distributors to the Australian Energy Regulator has a range of information, but what we're really looking at is the data that's in here. And so here we have what we need to know the date and time of outages, the asset ID that's incorporated within where the interruption has occurred. And I'll return back to this because this is at the moment a point of where we're having some issues. Generally, this asset ID is a feeder, but it's not always. So each of the different distributors will often provide a different asset class when they report this to the regulator. We have reasons for the outages, weather and vegetation based on previous discussions with the project management committee were the ones that we determined to be probably the most likely. This doesn't mean all of them will be due to wind events, but that's the classes we've extracted for our initial database collection. We have some statistics on the impact, being the number of people, the duration of interruption, and whether it's a major event day. So that's the data we pull out of each of the reports and have aggregated into the initial database. We've also pulled out information on what the network structure is itself, and we do this through a bit of a combination of data that we're able to source publicly through the public asset location information, which some of the providers have freely available online, and we have sourced for all the other distribution networks through Rosetta Network Map, which is a company that many of you will actually use to do the mapping of your network. And really the reason for doing this, so we don't actually need to know the location of every single asset on a network to do the analysis we want, but we do need to be able to identify where the assets that are listed within the interruption data, we have to know a location of those. And generally, sort of a plus or minus 5 kilometers is suitable for what we're trying to do, because, and the reason for that is because we're trying to link this with classifications of different types of wind event that have been made before by another one of our research partners. So Andrew Dowdy, who is at the University of Melbourne, has done quite a lot of work over the last decade or so using global reanalysis data to classify different types of storms and different types of windstorms. So the idea is if we know the location of the asset that's had the interruption or the fault, we can then link it back to these existing databases of severe wind events, and then we can classify the type of wind event that has caused it. And the types that we're really looking at is determining whether it's a tropical cyclone that has damaged the line, thunderstorms, fronts, east coast lows, and really also to identify whether the outage was due to something that was not a wind event, which obviously then we want to remove from the database. So the request I have for any of the distributors that are on in the seminar is that the IDs, the asset IDs we have within the RIN database are either feeders or zone substations off sometimes, but sometimes they're even at a larger aggregated level. But these do not match the IDs that we have within the asset maps for the networks that we have, or the network maps of the assets. And if we can't link the two together, then we can't actually assign the geographical location of the outage. So what I would ask for any of the people on the call is if you're able to share with the research team just the linkage between the IDs that get used in the RIN reporting to the IDs that are used in your network maps, that will allow us to make that link from one to the other and will allow us to continue. So if you are able to share that, that would be very, very useful. Otherwise, we have some more kind of roundabout and less accurate approaches that we can adopt. But if those direct linkages are able to be shared, that will be extremely good.
Sorry, Matt, can I ask, was there any particular businesses that were less clear than others, maybe?
There are some that we are able to get some information from, but I don't have the list of that in front of me, Craig, sorry. But I can definitely create a list of the ones where we're able to get all the information, which is actually none of them, some of the information and none of them connect. And I'm happy to share that with everyone so we can sort of
maybe,
ask
if you share that, I think that'd be helpful.
Yeah.
Okay. Yeah. Thanks.
And I did want to not leave this with not at least showing any answers, because we are actually able to draw some information just from doing an analysis on a distributor level. And so here I've just sort of plot up two. So one is Ergon, one is SA Power. So we've got sort of kind of rural Queensland and all of SA. And And really just to look at what I've shown here is the two different classifications we've pulled out. So whether an interruption was due to weather or vegetation. In Queensland, so for Ergon, you can see a very, very distinct seasonal change in it. And for someone that lives in Queensland like me, this makes perfect sense. When we come into spring and summer, we have lots of outages. This is when we have severe thunderstorms moving through the region. This is when we have tropical cyclones impacting the north. And as we get through winter, this is when we've got a much more benign and weather, so we have much less interruption. What was interesting here is that most of the things are, most of them are classified as weather, but there are some, and a relatively uniform number of outages classified as vegetation fall on the lines throughout the year. It was a bit different though in South Australia, where you have a much more uniform level of outages throughout the year. And certainly the split between vegetation and weather is quite different. And this could actually just be down to the way the different networks classify what they say is vegetation and what they say is weather. But this is something we can look into. And then the last thing which I found quite interesting was if we look to see when the outages are occurring, so whether they're on major event days or not major event days, the vast majority are not classified, are not on major event days, which I thought was, which was a bit of a surprise to me, but perhaps is not to some of the distributors on the line. But anyway, I think I will leave it there. So we do have a little bit of time for questions, and I'll maybe turn it back to you, Brendan.
Yeah, great. Thanks, Matt. Interesting results, and I think you're speaking a language that a lot of people on the call really understand. Penny, you've got your hand up. I'll throw to you for your question.
Quick question, just to find out what was the timelines on getting the information to you? Is that like a before Christmas task or a January task?
Yeah, I think obviously the sooner the better, but I'm not going to push you to do it before Christmas, Penny. No. Yeah, so January is perfectly fine. Yeah, we have, when we initially sort of set out the project, this was something that we had early on to start with, but because we've had a couple of these issues, we've just started doing other parts of the project so we can just shift it a little bit later. So January will be perfectly fine. And sorry, I see your question in the chat there. The idea is not within this project to do the vulnerability curves, but I'm happy to have a chat to you about that because I have a couple of other students working on doing that sort of alongside this project, but it's not actually part of the deliverable here. Yeah.
Thanks, Matt. Thanks, John, for going through that work this morning, or today. I think it's been really interesting. I think it gets down to an interesting level of detail, sets up pretty well what the project is looking to do. And I really like taking the opportunity just to reach out to everyone on the call. If you've got that information that Matt and team are seeking that can help, please pass it on. More information, the better. Excellent. Well, thank you very much again. Thanks for joining today. As we noted in there's a couple of reports which are underway, which are nearly done. And once we get those through, we'll make sure that we make those available, whether it's through the website, and you'll probably find someone like Craig will let you know that it's there and share those kind of things around. So thank you very much for attending today. Thank you for your interest, and looking forward to you being able to use the results of the work that's going on.